Welcome to Dr. Shashi's Math Mantra channel. Today we are doing simultaneous linear congruences and Chinese remainder theorem. Now, what are the simultaneous linear congruences? A system of simultaneous linear congruences is a set of linear congruences. A1x is congruent to B1 modulo M1, A2x is congruent to B2 modulo M2, A3x is congruent to B3 modulo M3, and so on. ARx is congruent to BR modulo NR. In general, every set of simultaneous linear congruences need not have a common solution. For example, x is congruent to 5 modulo 6 and x is congruent to 7 modulo 15 have no common solution. Then, what are the conditions that this system of equations have a common solution? For this, we have the Chinese remainder theorem. Chinese remainder theorem suggests under which conditions the system of linear congruences has a common solution. Practically, we can use theorem to solve the problems like find all the integers that give the remainder 1 to 3 when divided by 3, 4 and 5 respectively. So let's state the Chinese remainder theorem. Let M1, M2, Mr denote R positive integers that are relatively prime in pairs. What is the meaning of relatively primes in pair? It means that M1 and M2 are co-prime, M2 and M3 are co-prime, and so on. Mr minus 1 and Mr are co-prime. Means when we took any two M1 and M2's Mi's, then they will be co-prime. And let A1, A2, so on AR denote any R integers. Then the congruence is x is congruent to AI modulo Mi, I varying from 1 to R have a common solution. Any two common solutions are congruent modulo M, where capital M is the product of M1, M2, M3, so on up to Mr. So we will prove that this congruence have the common solution, these congruences have the common solution, and any two common solutions are unique up to the modulo capital M. So let's prove the Chinese remainder theorem. Now we have the given congruences that are x is congruent to AI modulo Mi, where I varying from 1 to R. We can write it in this system that x is congruent to A1 modulo M1, x is congruent to A2 modulo M2, x is congruent to A3 modulo M3, so on. X is congruent to AR modulo Mr. Let it be the equation numbers 1. Now, let capital M is the product of these all Mi's, that is capital M is equal to M1 into M2 into M3, so on up to Mr. Also let capital M1 is equal to M over M1, that is it is equal to the product of M2, M3, so on up to Mr. That means in the capital M1, small m1 is missing. Similarly, we take capital M2, that will be capital M divided by M2. So it is the product of M1, M3, so on up to Mr. Similarly, we define Mr, that is equal to capital M over the small mr, that is M1, M2, so on to Mr minus 1. That is product of M1, M2 up to Mr minus 1. Now, we can check that all the capital Mi's, that is M1, M2, Mr, are integers. Also, they are relatively prime in pairs with M1's. So, capital M1 and small m1 are relatively prime. Capital M2 and small m2 is also relatively prime. capital MR and small mr have the GCD 1. Now we consider the R congruences given by MIX is congruent to 1 modulo MI, I varying from 1 to R. Let it be the equation number 2. Now each of the congruents given by the 2 has exactly one solution. That is, X is congruent to Xi modulo Mi. Because Mi capital and small mi are relatively prime. Again consider X is equal to sigma I varying from 1 to R capital Mi into Xi into Ai. That is, capital X is equal to capital M1 small x1 into A1 plus capital M2 into X2 plus A2 plus so on MR, XR, AR. Let it be number 4. Now we shall prove that X given by this 4 is a solution of the first of the congruence given by the system 1. That is, we will show that this X will be the solution of the congruence. X is congruent to A1 modulo M1. For this, we know that M1 divides capital M2, because what is M2? It is the product of M1, M3 so on up to MR. Also, M1 divides capital M2 into X2 into A2. And this small m1 divides m3, x3, a3, and it also divides mr, xr, ar. So, m1 will divide the sum of all these, that is, m1 divides m2, x2, a2 plus m3, x3, a3 plus so on mr, xr, ar. Let it be the equation number 5. Now, from 2 and 3, x1 is a solution of m1x is congruent to 1 modulo m1. This is the number 2 and this is number 3. So, we get x1 is the solution of m1x is congruent to 1 modulo m1. Therefore, m1x1 is congruent to 1 modulo m1. Now multiplying the above congruence 6 by a1, multiplying this by a1, we get m1x1 a1 is congruent to a1 modulo m1. So from by definition of the congruence, we can say small m1 divides capital M1 x1 a1 minus the a1. So from this equation number 5, that says m1 divides this sum, and the equation number 7, we can say that m1 divide m1 x1 a1 plus m2 x2 a2 plus so on plus mr xr ar minus the a1. But this whole thing is the capital X, so we write here as the capital X. Thus we get m1 divides capital X minus the a1. And again we use the definition of congruence, that will give X is congruent to a1 modulo m1. Therefore, X is a solution of the first of the congruence given by 1. That is, X is the solution of X is congruent to a1 modulo m1. Similarly, we can find that X is also a solution of each of the congruences of 1. So that X is a common solution of the original congruences 1. That is, X is congruent to AI modulo Mi, where I varying from 1 to R. Thus in this way we get a common solution of these congruences. Now we have to prove the uniqueness part up to the congruences. So let X and Y are the two common solutions of the congruence 1. congruence is 1. Then x is congruent to ai modulo mi and y is also congruent to ai modulo mi. Then by symmetric and transitive properties, we can say that x is congruent to y modulo mi. Also, all mi's are relatively primes in pair, thus LCM of these mi's, I varying from 1 to r, will be their product. That is, capital M is equal to M1 into M2, so on up to MR. So we can say that capital X is congruent to capital Y modulo LCM of M1, M2, MR, and which is the product of these M1, M2, MR, that is capital M. So we can say X is congruent to Y modulo M, or Y is congruent to X modulo M. That is, the solution is unique up to the congruence modulo M. Hence the proof of Chinese remainder theorem. Now let's take this example that x is congruent to 1 modulo 4, x is congruent to 3 modulo 5, and x is congruent to 2 modulo 7. Means we have to find a number which when divided by 4 gives the remainder 1, divided by 5 gives remainder 3, and divided by 7 will give the remainder 2. So for this we take these congruence, first congruence, that is x1 is congruent to a1 modulo m1. In the these congruences we have a1 is equal to 1. If we compare it with the xi is congruent to ai modulo mi, where I varying from 1, 2 and 3. Then a1 is 1, a2 is 3 and a3 is 2. Or m1 is 4, m2 is 5 and m3 is 7. First of all we will find this capital M, that is equal to the product of m1, m2, m3. So it is 4 into 5 into 7, that gives you to the 140. Now we find capital M1, that is capital M over the small m1. So it will come out to be 35. And M2 will come out to be capital M over M2 as 28. And M3 will come out to be 20. So consider this congruence. M1x is congruent to 1 modulo M1. That is 35x is congruent to 1 modulo 4. Now we have 0 is congruent to 36 modulo 4. So adding these we get 35x, subtracting these two we get 35x is congruent to minus 35 modulo 4. Now because 35 and 4 are co-prime, therefore cancelling 35 we will get x is congruent to minus 1 modulo 4. To make it positive we know that 0 is congruent to 4 modulo 4, and adding these two we get x is congruent to 3 modulo 4. So in this way we get x1 is equal to 3. Now to find the solution of next congruence, that is x is congruent to 1 modulo 5. Consider this, m2x is congruent to 1 modulo m2. Since m2 is 28, so we get 28x is congruent to 1 modulo 5, or 0 is congruent to 55 modulo 5. So adding these two we get 28x is congruent to 56 modulo 5. Since again 28 and 5 are co-prime, therefore x is congruent to 2 modulo 5, because 28 will cancel from here. So the solution of the second congruence will be x2 is equal to 2. Now for the third one, m3x is congruent to 1 modulo m3. m3 is 20, so 20x is congruent to 1 modulo 7. Now again we have to take the nearest to 20, and when we adding or subtracting this number and this number, we will get a number which is co-prime to 7 and multiple of 20. So here we can take the 21. So we get 0 is congruent to 21 modulo 7. Then adding, subtracting these two, we get 20x is congruent to minus 20 modulo 7. Now 20 and 7 are co-prime, so we can cancel. Therefore x is congruent to minus 1 modulo 7. Again, to make it positive, we get 0 is congruent to 7 modulo 7. Therefore x is congruent to 6 modulo 7. Thus we get x3 is equal to 6 is the solution of third congruence. Now to find the common solution. Now let x is equal to m1 x1 a1 plus m2 x2 a2 plus m3 x3 a3 by the Chinese remainder theorem. So that is equal to 35 into 3 plus 1 plus 28 into 2 into 3 plus 20 into 6 into 2. So it gives 513. Adding these three numbers, we get the 513. Now x is congruent to 513 modulo 140. So dividing 513 by 140, we get 3 is the quotient and remainder is 93. So we can say x is congruent to 93 modulo 140. Thus we get the number 93, which when divided by 4 will give the remainder 1, divided by 5 will give the remainder 3, and divided by 7 will give the remainder 2. Thank you.